case. Oh, I had assumed that I'd started recording. I'm sorry. Okay. Right. So, but this is the simple setup where we are using independent Bernoulli random variables. Okay. And in this space of Bernoulli random variables, we also defined a bunch of other random variables. Okay. Now, this setup is very common in all problems with estimation and so on. You have a probability space on which you have defined a bunch of different random variables. Oh, James, you have a question?
Yeah, we can't see your screen anymore.
Oh, how did that happen? Okay, better? Okay, yeah, thank you. Right, so you have a probability space on which you have defined a bunch of different random variables. Okay, now here we have assumed that somebody magically gave us these parameters of the various Bernoulli random variables. Okay, now, usually that's not the case. Right? So usually the fact that we are modeling as independent Bernoulli random variables, that part is something we do as an assumption, okay? And that is based typically on like something else that we know about the problem, okay? But once you have this, you want the data to tell you whatever you need to know, okay? So for example, like you're throwing a bunch of, you have a coin and you want to figure out what is the bias on this coin, okay. We had this example where we were looking at the prevalence of colon cancer, okay. Now in all of these cases, right, so what you have is like some general setup of the problem, okay, but you don't usually have quantities like this given to you, okay. This p being given to you is unrealistic. Okay, it is okay to model it as independent Bernoulli trials when you're tossing a coin a bunch of times. Okay, because you're not, so long as you're tossing the coin a bunch of times, like it is fair to assume that these coin tosses are, or fair to model, not assume. Okay, it's fair to model these coin tosses as independent. Okay, but the parameter is something we typically want to infer. Okay, so you could infer the parameter p. So the more realistic thing is that x1 through xn are independent Bernoulli trials. Right, we do not know the parameter. Okay, so we may even assume that all with the same parameter, which we do not know. Okay, and now we observe some data, and based on this data we want to infer this particular parameter. Okay, so for example, like if x1, so what would be a good way to infer this parameter? So you have seen n trials. Okay, there are at least two different ways we know how to infer this parameter. Okay, there are okay, so we want to infer. Okay, so let us say, so what we do is like we estimate using x1 through xn. Okay, we have some estimation of this parameter p that we are interested in using the samples that we have seen so far. Okay, now what would be a good estimate for p? Okay, so let's call our estimate. So number one, our estimate is a function of Our estimate is a function of the data, right? So whatever our estimate is, okay, it's a function of x1 through xn. Okay, which means like once we have seen x1 through xn, that's what we are going to use. We don't have some other side information, right? And we'll call this p hat. Okay, and we want, the reason is like the distinction between p and p hat is that p is some unknown quantity that we never get to see. Okay, p is some number that we never get to see. Okay, the best we can do is we can look at this data, and from this data we can output a function of this data. Okay, and our output is p hat. Okay, now p hat may or may not be equal to p. It may not even be close to p. It may not even be it may not even be close to p. Okay, so it depends on how much the data has fooled us. Okay, the data could fool us, or the data could actually give us the some information that is reliable. Okay, but we are at the mercy of whatever we see. Okay, now, so but p hat is what we have at the end of the day. Okay, what we observe at the end of the day. Okay, now can you give me a couple of different ways to compute p hat?
You could sum across x1 to xn and then divide by n.
Very good. Why is this? Okay, so let us say the first estimate is p hat, and Caleb says, okay, sum x1 through xn and divide by n. Okay, and why do we like this estimate? How do we believe that this estimate will function?
It's just a simple average that given enough trials, you could possibly assume that it's likely that it would approach the true value of t.
Right, so that's very good, but let's try to make it a little more formal. Okay, so here we may not know the parameter, but we do know x1 through xn are independent Bernoulli triads. Okay, so this would have been equal to the binomial variable run by n, okay, divided by n. Okay, so but we do know how yn would behave. Okay, we know how yn would behave as a function of p. Now, of course, we don't know p. Okay, but subject to, with that caveat, okay, we do know how yn would have behaved with respect to p. Okay, but we know some other things. What is the expectation of yn? Right, so I've written it just above. What is the expectation of yn? Right, so n times p. I do know that on an average, yn will be n times p. Okay, so what is the expectation of p hat? Okay, now before you answer, like couple of things I want to point out. Okay, p hat is a function of the data. Okay, so our estimate is also a random variable. Right, so our estimate is a random variable. So because it's a random variable, okay, we can ask for its expectation. Okay, it's just like any other random variable that we have been looking at. Okay, except like we have a story to hang on it, that we see data and we compute some function of the data. Okay, but if you ignore the story, it's just another random variable. Okay, okay, so what is the expectation of p hat? Right, so in general, like we know a few things about expectation. If x is a random variable, what is the expectation of a times x, where a is any constant? Yeah, a times expectation of x. Okay, so what is the expectation of p hat? Expectation of p hat is the expectation of yn over n. Okay, and the if we want to do it again, this is x1 plus x2 all the way through n over n. If you want to use so this is 1 over n times the expectation of x1 xn. This is 1 over n times the expectation of x1 plus right. So this is each of these is p, right? So this will be just n times p over n, which is p. Okay. Right. Let me just change the. Just give me a second. Okay. Right. Let me just do one thing. Okay. So is it better now? Is it better with the audio?
Yeah.
Okay. Okay. Yeah. Sorry. Like I think like at some point a microwave starts and that destroys like my internet setup. So anyway, right. So going back, like let me just repeat this. P hat is a random variable. Okay. So P hat is a random variable. The story behind it is that we see x1 through xn, which are random variables, and we compute p hat from them. Okay, and as a consequence, p hat is also a random variable. Because it's a random variable, we can compute its expectation. Okay, and when we compute its expectation, right? So we are just going to use properties of expectation we know. Okay, and in this case, if you compute p hat as x1 plus x2 all the way through xn divided by n, okay, you're going to get that the expectation of p hat is going to be p. Okay, so this is one reason this is a reasonable estimate. Okay, this is one reason why averages are reasonable estimates of the parameter. Okay. Value of the parameter. Okay. Now this is not this is not thoroughly satisfying because who's going to take n samples once, compute p hat, take one n samples again, compute p hat again, and do it like many times. Okay, so that's not very reasonable. Okay, but lucky for us, there's actually more. Okay, we will be able to say a little more about how p hat behaves. Okay, and that is because we know the uh, way that the binomial random variable yn is distributed. Okay, so here if we plot on the x-axis, okay, on the x-axis I'm going to plot p hat. Okay, the various values. So when I say plot p hat, I mean the various values p hat can take. Okay, what are the various values p hat can take? Remember n trials, and p hat is the average of all these n trials. What are the various values p hat can take? They all
Like
possible.
zero through n, right?
No. What p hat cannot take the value n. What's the highest value p hat can take?
1.
1.
Yeah, right? Because we normalize by n, right? So the values p hat can take are 0, 1 over n, 2 over n, all the way through 1. Okay, so these are the different values it can take. Okay, and what I do is, like, on the x-axis, I'm plotting the various values that p hat can take. Okay, on the y-axis, I write the probability with which it can take each of these values. Okay, and this curve, we know how it looks like. So the probability p hat equals k over n is exactly the probability yn equals k. And this is m choose k, p to the k times 1 minus p to the n minus k. Okay, and there are, so this is usually non-trivial to compute. Okay, and the computation is not very easy. But there are some things that I can tell you. Okay, so this will be concentrated around the value p. Okay, so this particular probability, when I look upon it as a function of k, it has its maximum. Okay, when k over n is roughly equal to p. Okay, so remember, p is some number, not necessarily a rational number. Okay, so this hits a peak around the value of p. Okay, it's not symmetric around k equals n. Okay, it's not particularly symmetric. Okay, but when you don't deviate too far from k over n, it looks somewhat symmetric. Okay, if you go too far away from k over n, the symmetry is broken. Okay, now the variance. So this is the probability of, so this is going to be, in fact, like, I'm drawing it as a smooth curve, but in reality, this will be the probability of various numbers. Okay, we are going to see it. Don't worry about my plots, we'll see it in simulations. Okay, so but this, this curve that I've drawn just connects together all these various values of probabilities. Okay, now in addition, okay, the variance of y, the variance of yn, or let's say the variance of p hat. What's the variance of p hat? Right, so this is the, we know the variance of n, so this is the variance of yn over n. Okay, this is 1 over n squared times the variance of yn. Okay, and we know that the variance of yn is n times p over 1 minus p. Let me move this. Okay, so the n and n squared, the n cancels with one of the n's in the denominator. So the variance of p hat is p times 1 minus p divided by n. Okay, which means larger the number of samples I take, the smaller the variance. Okay, and the variance controls this width. Okay, so p hat is random, true. Okay, and p hat can take on various values with different probabilities. Okay, now the width I'm drawing informally right now. Okay, let us say that I take all values of probability, okay, all values of that p hat can take, okay, that have at least probability like 1 over something of the maximum probability, okay, or in other words, like I want to take a set of values for p hat around k over n, okay, so that the area under the curve in this region is close to 1. Okay, so this area, so I want this area to be significant. Okay, so this area, I want this to be close to 1. Okay, we are not being very specific about close to 1, but you can say it is at least greater than 5/6, let us say. Okay, so this means that with probability 5 over 6, my estimate will fall into this zone. Okay, now what happens, the way the variance comes into play is that the variance controls the size of this width. Okay, and in fact, like the size of this width is going to be something that depends upon the square root of the variance of p. And we have a name for this. We usually call this the standard deviation of p. Okay, and so this is going to be, in our case, something like 1 over square root of n. Okay, so in a sense, you're going to see while p hat is random and technically could take on every possible value from 0 to 1. Okay, in reality, what happens is that you usually see values within a certain number of standard deviations away from the mean. Okay, so you won't deviate by more than a few standard deviations from the mean. Okay, and if n is 100, this is roughly 0.1. Okay, 1 over square root of n. Okay, so 1 over 100, so this is roughly 0.1. Okay, when n is 10,000, right? So this is 0.01. Okay, so this means that the larger the number of samples, okay, the less your deviation of the estimators from the true value. Okay, so that means you can keep your true value as a better and better approximation to the true parameter the more the number of samples you take. Okay, does that make sense? Right, so any questions? Okay, so right, so at this point, like it's also useful to formalize something else. Okay, we could also in this space, right, like okay, so you could do something like this. Okay, so let's do. Okay, so you have n samples. Okay, let's consider two different random variables. Okay, y n over 2 is the sum of the first n over 2 samples. Let n be even. Okay, we're not going to worry about whether n is even or not. We'll just assume that n is even. Okay, okay, and yn is the sum of all the samples, average of all the samples. Okay, now these are two different random variables. Okay, what can you tell me about yn from yn over 2?
Would it likely have a smaller variance?
That's true. I'm actually asking a different question. Can you estimate yn? So let us say that now we are so in the previous example, right, here we wanted to estimate this fixed number p, the parameter p. Okay, right, so Right. So Donovan, I'll just come to you. Okay. So here, I don't want to estimate a fixed number. Okay. So here, my question is a little bit different. I want to estimate yn from yn over 2. Okay. I want to estimate one random variable from another random variable. Okay. Now yn itself, it's not a fixed number. Okay, once we have seen x1 through xn, yn gets fixed based on x1 through xn. Okay, but yn in general is a function of x1 through xn. Okay, but yn over 2 has only seen x1 through xn over 2. It hasn't seen the remaining random variables. Okay, so just because just because, like, let's say that you get to see yn over 2, I get to see yn. Okay, because I've seen all the bits x1 through xn, yn is a number. Okay, yn is a number. Like once I've seen x1 through xn, yn is just a number. Okay, but before I've seen x1 through xn, yn could be any number from 0 to n. Okay, there are probabilities for it can it is equal to k. There's probability it is equal to n, and so on. Okay, but every number is possible. Okay. So, but what I want you to tell me is not the probability distribution over yn or anything like that. Okay, I want you to tell me what is yn. Okay, so it's like trying to hit a moving target. Okay, yn is not a fixed number. Okay, yn is a random variable, but you're trying to figure out what the value of this random variable is. Okay, and how do you do that? You have some partial information about yn. Okay, and that is yn over 2. Right? So let us say yn over 2 was 0. Okay, so what would be the estimate for yn? Okay, so suppose yn over 2, or okay, let me actually write this as so Donovan, like, I think, okay, now I see there may be a potential for misunderstanding. So let me write it like this. Right, I'm going to write it like this, 2k in this one, because the way I write n over 2, it may look like yn divided by 2. Okay, I don't mean that. I mean y2k and yk. Okay, right? So it's like yk sees samples x1 through xk, y2k sees samples x1 through x2k. I want to figure out y2k by seeing yk. Okay, and this is like a typical scenario for us. Okay, we want to estimate one random variable by observing another random variable. Okay, so for example, like, let's just parse this a little more. Suppose yk turns out to be 0. Okay, what would be the best estimate? What is a good estimate for y2k? Would it be 0? So explain to me why you would say 0.
I just don't see a way that you could change it to not be 0. It just doesn't seem like mathematically possible, or it seems difficult to.
No, it's actually a good answer. 0 is actually a fairly good answer. It's actually a very good answer. Okay, but why did you say 0?
Just, I feel like if we cut the sample space, like if we like have like half the iterations or 2k or even more, I feel like it still should be similar, right?
Okay, so and also tell me what you told me before. So in general, what would be your estimate of y2k? Let's call our estimate, we'll call our estimate y hat 2k. Okay, because what we estimate may be different from the true value. Okay, and you told me something else. You said y hat 2k was 2 times y of k, right?
Yes.
So this is actually a very good estimate. Okay, why is this? Why would this be a good estimate?
Just twice the sample space, so it would be twice the probability, or not probability, but the value of it would be twice.
Okay, so one way to see this, is that okay. So let us say that. So all we know here again. Uh, let me just write it. X1 to X2k are independent. Oh, no, sorry, these are averages. My apologies. So these are averages. So uh, okay. So you're almost okay, but it's kind of my fault. Okay. It's kind of my fault. I changed the notation on you. Didn't intend to do that. Like I was just writing a little bit of a brain freeze. Okay. Let's take yk to be just the sum of the first xk random variables, because that's the notation we have been using. I didn't mean to change the notation on you. Sorry. Okay. And y2k is the sum of the first 2k random variables. Okay. And we want to estimate y2k from yk. Okay, and the estimate Donovan tells us is we are going to try and estimate y2k as 2 times y of k. Okay, and why is this? This is actually a very good estimate. Okay, the reason is like x1 through xk, x2k are independent. Okay, let's take y. Let's look at yk. Yk depends on x1 through xk, and then there are these random variables xk plus 1 to x2k. Okay, now we are going to call this zk. Okay, the sum of all of this. Zk is the sum of xk plus 1 through x2k. What sort of a random variable is zk?
Like additional from like not the first space. So what we're trying to estimate from our
Right,
given.
zk. So no. My question is even more basic. Like, what sort of random variable is zk? Okay, so zk is the sum of k Bernoulli independent random variables. So what is zk? Yeah, it's also binomial. It's exactly a copy of yk. It's like an independent copy of yk. Okay, so it's also binomial. It has parameters k and p, which we do not know. Okay, and yk also is the same. Okay, so what is happening is that y2k just happens to be the sum of yk plus zk. Okay, now we have seen this. Okay, but we haven't seen zk. Okay, we haven't seen zk, so the things we haven't seen, I'm going to write them in red. Okay, we haven't seen zk. Okay, so we need to guess the value of zk. Okay, now we don't know if we knew the parameter. Okay, if we knew the parameter p, we could say zk is k times p. That would be a good estimate. Okay, because it's the expectation of zk. Okay, but we don't know the parameter p. Okay, so here a very interesting suggestion is that we are going to estimate zk as simply yk. Okay, we just notice yk and zk are distributed in the same way. We have seen the value of yk, so we are just going to estimate zk with the same value. Okay, that will give us y2k to be 2 times yk. Okay, it's a very logical way of thinking, but we want to formalize this a little more. Okay, so okay, right, so here is what we do. Okay, so if you wanted to estimate zk by a number, Okay, we know how to do this. Okay, if we wanted to, this example will actually tell us a few different ways about thinking about this problem. Turns out that in order to think about this problem, this is not the only way. There are many different ways we can actually think about this problem, and they're all valid. They're all different techniques that people use. Okay, let's start off with something we know about expectation. Okay, if we wanted to estimate some random variable z with a number, okay, what is the number that we would have used? In the mean squared sense, right? If we wanted to estimate a random variable z, okay, with a single number, okay, in the mean squared sense, what was the best number we could have chosen? We did this a few classes ago, okay? So I'll link to that class so you can review. The best number to use is actually the expectation of z. Okay, the single number that best captures the random variable in the mean squared sense is its expectation. Okay, and in the same way, here we are going to define the best estimate of y2k from yk will be this is something we need to parse a little carefully. This is called the conditional expectation of y2k given yk. Okay, now our estimates are random variables, so this is not a number. Okay, this is a random variable. Right, so in general, this is a function. In general, this is a function of yk. Okay, in general, this is going to be a function of whatever value yk has taken. Right, and this quantity, the expectation of y2k given yk, it's called the conditional expectation of y2k given yk, and it's typically a function of yk. Okay, so this generalizes our previous observation that the best single number that captures a random variable is the expectation. The best estimate of one random variable from another random variable is the conditional expectation. Okay, so we are going to pay a little bit of attention to this conditional random variable. Okay, but let's try to do something. Okay, so let us say that let's go back to a simpler setting where x1 through x2k are now known to be independent Bernoulli P random variables. So this time we know the parameter P. Okay, let's say we know the parameter P. Okay, so what is the probability of y2k given okay, what's the probability distribution of y2k, the random variable y2k, conditioned on yk equals n? Okay, so what does this mean? Here, this means that we know that yk equals n. Okay, what are all the values that y2k can take?
Be 0 to 2m, right?
No, can it take value 0? Let us say m equals 10. Yk is 10. can y2k be 0?
It would be from y sub k to y.
Right. Right. So in this case, it can take values from m. M is the smallest value that y2k can take. Right? So what is happening? Like x1, so x1 through xk, this is yk. Okay, and y2k simply adds on to it another k random variables. Okay, so this part of the summation is already m. Okay, you cannot have the sum of all these 2k random variables to be anything less than m. Okay, because each Bernoulli random variable is only 0 or 1. Okay, the smallest value y2k can take, given that yk equals m, okay, happens when all these random variables are 0. Okay, because you already know yk equals m, you have lost control of what has happened to x1 through xk. Okay, those things are already given to you, and their sum is m. Okay, now the only randomness is in the remaining xk plus 1 through x2k. Even when they are all 0, y2k is now still m. Okay, right? So if yk is m, okay, the different values y2k can take are m plus 1 all the way through m plus k. These are the different values that y2k can take. Okay, is everyone okay with this? Okay, so right. So what is the probability that y2k equals, let's say, m plus r, where r is some number from 0 to k? Sorry, probability m plus r given yk equals m. R can be smaller or larger than m. R can be smaller or larger than m. Right? In fact, R ranges from 0 through k. Okay, so it's something like this. Like, let's say x1 equals 0, x2. Let's do like a numerical example. It will be easy. Let's take k equals 3. Okay, so 2k equals 6. Okay, the first three trials are x1 is 1, x2 is 0, and x3 is 0. Okay, so yk, what is yk? Right, yk is the sum of the first k random variables. The first three random variables are 1, 0, and 0. Okay, so what is yk? Why 0? It's 1, 0, and 0. Right, so yk is x1 plus x2 plus x3, which is 1. Okay, now we know yk is 1. Okay, what are the, oh yeah, okay, never mind. So what are the values that y2k can take?
Oh, hold on. Would that mean that 1 is equal to m? Wait, from like the earlier, so when we were saying
Right.
like yk equals m, like,
Right.
is that the
M is
number?
right. M is the value that yk has taken. So m is a number. Okay. M is the number that is the value that yk has taken. Right. So now I haven't revealed x4, x5, and x6 to you yet. Okay. So but that means, but because you already have seen x1, x2, and x3. Okay, this means that y2k can now take values 1, 2, 3, and 4. right? That's exactly what we have written, m through m plus k. Okay, and now I want to know what is the probability with which it can take each of these values. Okay, and that goes by a simple binomial model on x4, x5, and x6. Okay, so the probability x2k is equal to m plus r is therefore the probability of seeing exactly r once among x4, x5, and x6, or among xk plus 1 through x2k. Okay, and so this is k choose r, p to the r times 1 minus p to the n minus r, k minus r. Okay, so the probability here, for example, that y2k equals 1 plus 2, okay, or 3, given that yk equals 1 is the probability that exactly 2 of these 3 random variables turn out to be 1. Okay, and so that is 3 choose 2 times p squared times 1 minus p. Okay, so we'll continue next class from here. Okay, review this particular problem and make sure you understand the conceptual setup behind estimating one random variable from the other. Okay, and the next class we are going to do it in a few different ways. We are going to estimate this in a few different ways. Okay, we're going. Okay, so we'll continue next class. So any question, you can continue asking questions.